Yeah, sure.
Yes. Okay. Good afternoon, everybody. And many thanks for the organizers for inviting me here. I know Camerino, of course, from the physics very well, but I have never been here, so this is really an honor and a pleasure to visit here and give a talk. So I will talk about 3 different topics related to superconductivity, superfluidity. First, something that is somewhat connected to the previous talk about, well, if you take a perturbation in 1D gas and move it through the gas, what happens? Then second topic is about the SFLO state, and there we have focused on non-local quantum fluctuations beyond meeting. And the last one will be just a small snapshot because that's unpublished work, still very much in works, but this you can find in the archive. And here I just got some other works that we have done recently. If some of you is interested in one of these topics, you can come to discuss with me during the poster session. I will be leaving tomorrow morning, so if you have something in mind, also questions to my talk, please discuss today. Okay, so let's go to the first question. So, as we learned from the previous talk, or maybe from our courses, there is a so-called Landau's criterion that if you have a superfluid flowing through a pipe, then you might or might not create excitations, and the critical velocity for that process is this one. For bosonic condensates, there is a linear dispersion, so actually the critical velocity is then the speed of sound. And there have been many measurements on this concept in ultra-cold gases, and of course in helium and so on, but I don't know about those. But in ultra-cold gases, people have, and I think some of these are actually helium references. People have used vibrating wires, laser beams, etc. to try to create these excitations and probe the critical velocity. For a fermion superfluid, you know what is the dispersion, and then having this as the minimum energy difference, when you create an excitation, one derives this Landau's criterion, as was already told. Okay, and this criterion tells that below the critical velocity superfluid should be preserved and above it should be broken. Okay, so we thought, okay, what about considering a problem in 1 dimension where we try something similar? And we have a method with which we can do exact simulations of the quantum dynamics of this system. So now I'm going to present exact results. So it's like doing an experiment, so to speak, but at 0 temperature this time. So we have a 1-dimensional system with overall periodic structure. Then we have 2 components there, like spin up and spin down fermions, and with attractive interaction, so that you form pair correlations, as is known for 1D systems. So this blue and red are sort of describing the pair correlation. Then we take a Gaussian well or Lorentzian potential and run it through the system with velocity v and see what happens. And now you can make a guess in your mind what will happen when we do it with different velocities. So I will show you what happens, but think of it yourself. Okay, you got the answer. So the model is the usual Hubbard model, and we have the harmonic track as usual in ultra-cold gases. And then the Hamiltonian is time dependent because we had this perturbation going through the system. Here are basically the results. So now we describe here density profiles. This color is up particles, this is down particles. And this is the doublers, 2 particles at one side. And the potential well is depicted here, or the barrier. Now if we have a slow velocity for this barrier, you can see from this picture, here the barrier is in the beginning, here it's in the end, and from this picture that the gas is very much deformed. So a lot of things happen for small velocities. Whereas if the velocity is fast, we see almost no change to the density. So let's look at something else than densities, namely the singlet superfluid correlation. And it is known from exact 1D theories that if the Latin parameter k rho is bigger than 1, I mean corresponding to attractive interactions, then these pairing correlations exist and they decay polynomially. So this is so-called 1D superfluid, the equivalent of the usual superconductor in 3D, but now with a polynomial correlation, so no long-range order. And this is how the correlations look like at the ground state. And now when we move through this perturbation, first slowly, or let's say first fast, we see that correlations preserve in this case. And then when we move it slowly, this velocity, the correlations completely disappear. Superfluid is destroyed. And then in the fast regime, we see that the only thing that happens in the system is that there will be a phase change, a phase imprinted. So this is the phase of the pair correlation function. That changes where the potential is moving. So it's like phase imprinting. Whereas in slow, well, the phase is completely messed up. And we can quantify the phase in a very simple way, just the integral of the potential that we have. So you might want to know what is fast and slow, and it turns out that the relevant time scale here is that, well, there is attractive interaction and is lattice. So then these guys want to move as doublons. So there is a certain speed with which they can move, since they are bound together a bit. And this more or less gives what is slow and what is fast, whether it's bigger or smaller than this. Okay, so in the beginning I speculated that based on this lambda criterion and so on we would expect this thing, but we actually observed the opposite in this 1D system. For slow velocities, superfluid correlations are destroyed, and for fast they are preserved, but you imprint a phase. And one way to understand this is that well, these doublons have to move, and if the potential goes very slow, they try to go and fill it, and they are able to do it because it's so slow. But when it goes fast, the system cannot react. So that's actually one example that, well, after seeing these results, we dig the literature a lot to see how is superfluid density and critical velocity and so on defined in one dimension, and there are at least 5 or 6 different definitions. So this is an open question, and very counterintuitive results can be seen. Yeah.
Does this remain true even when the barrier has a very short width?
Yeah. We vary the barrier width, and it doesn't really matter.
Related question: How deep was the barrier here? Sorry, I missed that. It's like quite deep.
So deep, you mean?
Yeah.
Okay.
In terms of chemical potential or something.
Yeah, it was rather, I mean, yeah, certainly more than the lattice side. So it was considerable. It was quite big. Because we wanted to have here something like really like a wall going through. Yeah. But actually in the fast regime, it does not really matter. It just gives a bigger phase change, but the result is the same. So then I go to the next topic. And this is related to imbalance gases in ultra-cold gases and of course in other systems as well. So one can have now think about some pairing scenario, again spin up and spin down pairing, but think about having different numbers of ups and down and see what happens. So there is a lot of old theory understanding on this kind of thing. First of all, the Suntrasex-Croxton limit, which is saying that superconductivity is destroyed if you imbalance the system too much, if you have this chemical potential difference too big, the critical magnetic field. But there are then theory suggestions about other things happening, namely some kind of exotic superfluidity that could exist even in the presence of magnetization. This famous Fulda-Ferrell-Larkin-Ovchinnikov state, where the order parameter has a spatial dependence characterized by certain Q vector Q, which is basically the difference in the Fermi wave vectors of the two components. And then there are proposals about polarized superfluid states where you still have this magnetization, but no spatial oscillations and superfluidity. Well, there are some indications of people seeing these things. I think this has not been experimentally observed. So it's very interesting to think whether we could probe these states in ultra-cold gases and possibly realize them. But it's not even very well known how stable these are when you do something else than minting. Okay, so people tried these imbalance gases in ultra-cold systems. So they have fermions of two components and imbalance. Well, I don't explain what happened. It was basically phase separation, no FFLOC. These were three-dimensional traps. Then there is a prediction by my group that in a lattice, this FFLO state is very much stabilized and enhanced. And the argument is simple and easy to understand. Now, this would be the two Fermi surfaces in a free space. And you create this FFLO pairing basically by having Cooper pairs with finite momentum vector. In other words, you can think that you shift the Fermi the Fermi surfaces with respect to each other by some distance to Q to get them matched. So when you get them matched, you get pairing. Now in a lattice with certain filling, you might have rectangular Fermi surfaces. And then if you do this shift, you get a big overlap instead of this tangential touching. So it's basically the nesting that helps to stabilize FFLO in lattices. But this prediction was a mean field one. So we wanted to look at does this still hold if we include a bit more quantum fluctuations, and we did this with dynamical mean field theory, which treats local quantum fluctuations exactly. So it's basically a method where you solve in a lattice sort of a parameterized impurity problem exactly, and then you get some parameters and you put them back to the whole lattice problem and get some parameters here again and iterate. And the answer is yes, we still see it. So there are two papers where we showed that this is the case. But this was only the local quantum fluctuations. And now if you think that FFLO state is this kind of oscillating order parameter, one might think that, okay, maybe you really have to include a bit longer range quantum fluctuations. And this is our new results, can be found in arXiv, where we did cluster DMFT instead of the single side. And this means that this impurity that is solved exactly is not just one side, but it contains many sides. And then we sort of get the exact results for a bit bigger entity. And what was the cluster? that we solve exactly. In our case, it was like one dimension of this kind of three-dimensional lattice. So in other two, we still did the usual DMFT, and here we solved the cluster. And we see that, first of all, we see that when, I have to explain that then we also varied the hoppings, like that's why this thing, bond is thicker. We can have a bigger hopping here, and then if this is very big compared to this, we are in 1D, so we did 1D, 3D crossover. And close to the 1D, as you might expect, the fluctuations become very important. So this is the transverse hopping, this is the 1D limit. We can see that even for the normal BCS state, not any FFLO, there is a huge difference between the critical temperature of the single site calculation and the cluster calculation. And the nice news about FFLO is that we still see it here. It was not extremely easy to find, but we still find it. This is in scale of Fermi temperature, so it's not very high, but it's still not like ridiculously low. And here you can see how the order parameters look like. And we see that the local pairing dominates. So now we have the pairing, this is basically the anomalous part of the Green function as a function of the difference from one side. So it has some contribution also out of the one side, but it's dominated by on-site pairing. And here you see the more of the whole 1D, 3D crossover from 1D towards 3D. And okay, the BCS static mean field is known to give a rather bad result here close to the 1D limit. So this is the single side DMFT, already better than this. And then the cluster version, now this is inverse temperature. It starts to deviate over here. And here are the FFLO result. Here is a small curiosity that it seems like that the cluster version would predict FFLO in a higher temperature than the single side. But we are not totally sure about this. This would require more studies to make a claim.
Well, does it depend on the size of the cluster? So if you take a larger, smaller cluster, is rather changing?
We have varied the size of the cluster, at least not dramatically. Yeah. These are extremely heavy calculations, require supercomputers, so we could not vary it a lot, but at least we didn't see when we varied from, let's say, 10 to 20, 25. We didn't see anything dramatic.
Is there any significance to the change of slope of the FFLO after that is identified in both cases, single-sided cluster?
Yeah,
there's a change of slope.
Yeah, I don't know.
Is there any significance to that, or is that?
I dare not to make any claims. One should then calculate more data points and so on. Okay, so that was about the lattice. So the lattice is still promising, even if you really try to do your best with quantum fluctuations. And then we were interested in 2D systems. So like Chris Whaley was telling, he has this 2D pancake. So in this case, no lattice here. And could there be FFLO there? And this paper you can find. Okay, so, but before going there, let me review briefly what is the effect of dimensionality. So in 3D, it's known that FFLO in general exists in a narrow phase space. But as I showed in a lattice, this phase space becomes bigger. So lattice favors it. Also, some people say that spin-orbit coupling can help. In 1D, you always find FFLO, but there you don't have a real long-range order. It's this polynomially decaying order. And in in 2D, then much less is known. In lattices, again, yeah, there you can see FF and FF below. But what about this homogeneous 2D FF? And in this work, we consider this FF ansatz, which has just a single plane wave dependence in the order parameter for technical reasons. And we did not consider, for instance, this LO, not to talk about anything more complicated. And as you know, in 2D, we have to worry about the KBD physics, BKT physics, and there could be quasi-long range order below the BKT transition. And this transition temperature is defined by this relation where we have a superfluid density, and yeah, so below that we could do, if we find some FF phase, we could claim that okay, it is there. Above it, well, one has to do some much more involved studies. Okay, and I'm not going to go to any details, I just tell that we did the saddle point action calculation with Gaussian phase fluctuations and minimize the energy. And this is how the saddle point, so basically mean field, energy looks like, and this is the fluctuation energy with the spin wave type fluctuations. And there are parameters you don't need to know. The important things here is that one can calculate this analytically, and this is the result. And here we have a very strong temperature dependence for the fluctuations, and then there is superfluid density. And now what are XX and ZZ is very important. So we assume that this FF wave vector points to Z. So that's the direction of the FF modulation. And then X is the transverse direction. So you have to define the superfluid densities for both directions. And well, at zero temperature we found FF state, very nice. But at finite T, we found out that whenever you have the FF state, this transverse superfluid density becomes zero. So, and this we can show sort of analytically from the formula that this is identically so. So whenever we sort of break the symmetry in this direction by the FF state, then the superfluid in the transverse direction disappears. So this has to do with the symmetry of the system. But this is of course bad news for the FF state. So basically the fluctuations will kill it. And yeah, above BKT, this is another story. So, but this is not the end of the story, because there are some papers where, well, they didn't do the calculation that we did, but some based on some symmetry arguments. For instance, Rasikowski has claimed that maybe for the LO state, this disappearance of the transferred superfluid density doesn't happen. So LO would still be there. Or maybe with mass imbalance or some other tricks you could have it. But the simple FF state is killed by the phase fluctuations. And okay, you can have a look at our paper also, just forgetting about the FF state, because we have simply the phase diagrams for imbalance gas without any FF ansatz, and but with fluctuations. So people have calculated this already before with no fluctuation. They are these curves, and we see that fluctuations change it a lot around here, although below the BKT transition this seems to be the same. So here is normal, superfluid, and phase separation. So this is something that one could look at in these gases, the phase separation phenomenon. And temperature should be around here. This is in scale of Fermi temperature. Okay, and last couple of minutes, a few words about the nice multiband system that we have looked at lately, this has been experimentally realized in Hemmery's group for bosons. So they have a superlattice like this, and they can emit. And the basic point of this superlattice is that it has an S-band for one side of the superlattice and P bands for the for this deeper well. These hybridize and they produce almost flat bands, and we look at this system and do some well, actually we also introduce spin orbit coupling there, but this is not so essential here. And then we look simply S-wave interactions in this system. And now that we have many bands, the order parameters will be defined like this. This is the band index. We will have pairing for S band, this delta 0, for Y and Z, X, Y and X, and then XY pairing is delta 2. And we minimize the energy. And what we find out that this XY pairing is always 0. And then this S band and P band deltas exist, but they can have either the same sign or opposite sign. So this reminds very much of Ben Fattor's talk about their multiband case, and we have to really look at closer to this connection. And here are the phase diagrams as a function of magnetization. So we again put different numbers of ups and downs, and this is the spin orbit coupling parameter. So we see transitions from the same sign order parameters to the, okay, it's here, to the opposite sign order parameters. And what is remarkable here that at least in the mean field calculations, the critical temperatures are very high, about of the order of the bandwidth. So this is unusual because in many other scenarios it's like 1/10 of the bandwidth or something like this. And these have different orders. And we also try to look at the cell numbers. So this was all the physics, and now comes an advertisement. If you want to learn more about ultra-cold gases, for instance, you are from a different field and you want to know what is all this about, or if you are working in the field but you want to give the student a text where everything is really nicely pedagogically explained, you can buy this book, hopefully soon. So it's edited by myself and Klaus Sengstock. And here you can see some of the topics. For instance, Servas Kokkelmans writes about Fespach resonances, and I forced him to rewrite it twice to have a simple description of Fespach resonances at the same time detailed enough. And there are very modern things like this single site imaging. It's explained by great experts on that. And for instance, myself, I have a theory chapter, 50 pages about the spectroscopies in ultra-cold gases. I aimed it so that also experimentalists can understand everything. So no Green's functions are used, but it's fully many-body. So I recommend that. The conclusions are superfluids. In 1D, when we move this perturbation through, behaves a bit a funny way. It's destroyed for slow velocities and preserved for fast. Then we have shown that by cluster DMFT that even in presence of a strong non-local quantum fluctuation, the FFLO state is stable in lattices. But in 2D continuum, the fluctuations kill the FF state. And then we are working on a new type of multiband system. Okay, and here are some of the people who were important in these results. Thank you.
Thank you very much. We have some time for questions. Yes, yeah.
So one question was, when you could do the cluster DMFT, right? So, but were you still looking at S-wave states for the FFLO, or were there non-S-wave states?
They were S-wave. I mean, the pairing was S-wave on-site.
Yeah, because if you have cluster DMFT, you could conceivably look at non-S-wave.
Yeah,
Are you
yeah.
going to do that, or is there any possibility?
Well, we have extended our cluster DMFT to long-range interactions recently. Yeah, trying to see what happens there, and these other pairings are also possible.
Yes, Andrea?
In the case of multi-band superfluids, is it possible to consider a case of transfer pair terms? I mean, is it possible for a pair to jump from one band to the other, or with the ultra-cold gases is not possible? I mean, in multi-band superconductors, you may have Josephson-like terms, transfer
totally
pairs
possible,
from one band to the other.
Oh, okay, look at, yeah. So you can think that, okay, you have pairs here and pairs here, but they are the same type of atoms, so of course they can jump. So we have that term, this Josephson-like term there.
It should be possible.
Yeah.
What about this interband pairing? So a pair which is with one fermion in one band and another fermion in another band?
Not really, because then you would need, you could realize it, but then you need long-range interactions. Like if you want one sitting here, like between the P and S, then you would have one sitting here and another here, and you need the long-range interaction for that. So that is not there in this model.
I have a question about the first part. If you did it with repulsive lattice, would it be the same, or would that change?
You mean?
What does the attraction do? It causes these doublet formations?
Yes, we have not tried with that.
Do you think it would be different? Or? I also wonder what happens if you did it with a circular thing in a two-dimensional lattice.
I don't know. So in the Hubbard model at half filling there is this U minus U symmetry. But I don't know. I don't know what would happen. So what was the other question?
Just if you did a two-dimensional, you imagine a cylinder moving through, because then the particles can flow around, but they can't in one dimension.
Yeah. This is the difference. So I think the analog of our thing would be a sheet in two.
Oh, okay.
Which actually some people have tried experimenting.
Have you explored non-translation invariant correlation functions in the first part?
How would it, maybe you can see how it would be different from this one that could we look at. So you put some like momentum there, or? Yeah.
Can the C vary with space?
Here?
Does this depend only on, do you look at configurations that depend only on I minus J, or you study as function I and J separately?
Yeah, we have varied both of them separately, and it does not change much.
Last question.
I would like to ask for the lattice calculations. You are doing exact diagonalization or a mean-field approach, kind of Bogoliubov-Rosen calculation?
For the DMFT?
For the FFLO.
Yeah. Okay. In our old FFLO works, it was mean field, and in these new ones, the DMFT.
Yeah, but I mean the mean field to DMFT. Why? I mean, you do not explore the competition with different condensates at mean field instead of taking just one condensate and going to the DMFT level that is only adding the retardation. In principle, you should not play with, with all the parameters you are looking for.
Yes.
That's why you obtain more or less the same thing.
Okay, we have done in traps, we have more complicated order parameters, and in the lattice we varied the direction of the Q. So we have done a few playing around.
We have played a lot with these lattice models with Bogoliubov-Rosen. You can see that if you consider other condensates that compete, FFLO cannot arise. So this is that is if you consider only this type of S-wave of singlet condensate, then you have room for FFLO in some regimes, as you said, nesting helps. But otherwise it is not there, so it is not. So that's just a suggestion.
Yes, we have done also BDG, and we have varied the ansatz in the lattice as well.
Yes, so you can get more condensates on the ground.
I think we have to shift to the next speaker.